Hello, welcome to the fifth lecture of fifth tutorial session of quantum mechanics and molecular spectroscopy NPTEL 2024 session. And today is week 5. I am Prahlad Rajoduri and we will solve some assignment 4 questions. And let's start with a quick recap of the last tutorial, instruction video. And with this we will solve the with the help of this the equation and formula and some so we are just going to start the session today. So we will just have a quick recap of previous lectures, and from there we will solve the assignment 4 solution. Okay, so with this let's start today's session. I hope I am audible. Is my screen visible? Hello. Okay. So from the last from the first session, what we learned is that how a molecule excites. So we start with a simple two-level system where we we use time-dependent perturbation theory to find out the coefficient, and we found in coefficient how this molecule excited, and as we know, square of coefficient is the probability. So we found there is some oscillation and between the two state problem. Now the real situation is much more complicated, where it's not a two-level system, it's a many level system. So for n level of system, n is high in a large number. So we also derived the equation, and we found the transition moment depends on the main factor of the transition moment depends on the transition moment. It depends on the transition dipole moment. So which can be written as like this: for F h cut T I square, where the omega if is the difference between the two states. Okay, now if this is something that will determines whether excitation is favorable or not. Now if we dry gas it much more, then what we found, this F h comma T I integral is somehow proportional to F so in h comma T incorporates scalar and vector potential, which is a potential which is a form of a electric field and magnetic field. Now further doing this calculation, what we found for a transition from I to F, the expression of the probability of transition is something like this. Now this part actually takes about simulated emission, where this part is talking about absorption. So for only absorption case, and thing is that absorption and simulated emission cannot take place simultaneously. So both the phenomena will occur one at a time. Okay, so in case of absorption, yes, 0 to t. Okay, t indicates, so if this is a 0 to t, this is at the time duration when the light is on. Okay, at that duration light is on. Okay, so in case of absorption, the expression should be y square square now this is a constant term. This is talks about time transition dipole moment integral. This is talks about selection rule. Now what this part is says, so this is nothing but a delta function, but what is the expression of delta function we need to know. Now as I show earlier, so this is 0 to t at which the light is on, and if you think light is on between minus infinity to plus infinity, the actual time of light irradiation is not on, is only 0 to t. Okay, so 0 to t is nothing but minus infinity to plus infinity. Okay, now let's suppose delta a phi delta x and take as okay, so this is proportional to this, denote the e by h cut. Okay, and this is the angular frequency of light. Now if we write delta omega, then it can be written as limit t tends to infinity 1 by 2 pi sine delta t by 2 now as I mentioned this condition, so in the formula we can write it like that only, ft pi square e0 square h cut square one by 4 pi square sine square t by 2 square so whole integral will be e0 square 4h cut square sine square so this is the expression of a absorption. Okay, now so we can split it, this equation can we look at a 3 different section. This is a constant section, so this actually tells about the intensity of absorption. Next, this is, we all know that this is TMI, transition moment integral, talks about selection rule. Now what this is said, this is sine square x by x square. So if we plot, it will be look like with respect to delta omega and sine square if we write this is 0, that means when w fi is equal to w, so this is minus 1, this is plus 1, minus 2, plus 2, 3, 3. Okay, so this is kind of a damped oscillation kind of thing, and this actually tells about the line width of the spectra, and this is also a modulation factor. So this is the 3 parts that are incorporated in the probability of transition or absorption. Now, having this idea, it's enough to solve the first question. probability square by 4 cut square phi is fixed and depends on the energy difference between initial state and state to the omega phi varies as a function of the frequency electromagnetic radiation. Third, the time dependence of the probability of finding the system in final state if does not depend on delta mu. 4 EFT is modulated by sin square omega t equal to function. Now, so what is the first option is saying WFI is fixed. So WFI nothing but if there is two state, and I mentioned that the energy gap is delta Fi. So delta Fi is equal to H cut by WFI. So WFI is equal to delta EF by H cut. So as delta EFI is fixed, therefore omega Fi is also fixed and depends on the energy gap between two states. Okay, omega Fi is as a function of the frequency of the electromagnetic radiation. So I mentioned earlier the WFI naught is a incorrect option. Only omega is the angular frequency of the electromagnetic radiation. The time dependence of the probability of finding the system is in final state if doesn't depend on the delta omega. It's an incorrect option because you can see in the expression of the probability of transition delta omega is already incorporated. Okay, now as I mentioned previously, the from this plot you can say that the PFT is modulated by this sine square omega t by 2 by omega delta omega t delta omega by 2 square. So this is a modulating factor. This is a modulation. Okay, so for question 1 this is the correct these two are the correct options. Now for question 2, for the system described in question 1, the corresponding the condition required for the maximum probability of transition from initial state I and state F is or are resonance condition, that is the value of transition moment integral is 0. C Bohr frequency condition resonance condition So for this, as I mentioned earlier, if we plot the sine square with respect to delta omega, we will found maxima at 0 position, and with the progression the intensity will lose. So this condition, when delta omega is 0, this is known as resonance condition. So we know delta omega equal to omega a phi minus omega. So at resonance condition, for delta a phi is equal to, so when angular frequency of electromagnetic radiation matches with energy gap. Energy gap between I and F state. So this is resonance condition. So this thing is also known as Bohr frequency condition. So in this case there is first option is correct and this is should not correct, otherwise the transition will not happen. Third option is correct, this is Bohr condition when the omega a phi is equal to omega. That means energy gap between two systems is equal to the angular frequency of electromagnetic radiation. And we found that at the resonating condition or Bohr frequency condition, the omega a phi is equal to omega. So it is not. This is also not correct. The negative sign is there. Okay. So this is the answer of first two questions. Now let's moving to the third question. What we see? Yes. When the energy gap between two systems is matches with the angular frequency of the provided electromagnetic radiation. Hello. That is not zero time. I am talking not zero time. Time is something else. I am telling about the delta omega. Okay. So this plot is with respect to delta omega. Okay. So when the light is shined between 0 to t. Okay. Now if we scan with the difference between delta omega, which is a difference between delta omega a phi minus omega. So what we found, the profile looks like this. Okay. Okay. When the light is on, all the cases light is on. Yeah, in that is deviate from the that is the case. At that point resonance is not there. that there is a very weak transition, the modulation is very less. Okay, but at that resonating condition, the delta omega value goes to 0, and sine square x by x sine x by x term will shoot up to 1. Okay, so that is the reason it is only possible when x tends to 0. Means here delta omega is tends to 0. Here your x axis is delta omega. So therefore at resonance condition, this is only happen on the resonance condition. Okay, but throughout the time, when it is happening, the light is on. Okay. So number 3. The probability of transition or absorption from initial state I and final state A embedded in a density of states denoted by delta rho omega, sorry, E is given by So this problem needs little bit of understanding. So it's like previously we deal with n level of system where transition only happened between the I to F state, discrete transition between I to F state. Now let make situation much more complicated. Now what happens if the energy of a state gets higher and higher and higher? Now the excited states becomes embedded with so many closely spaced states. Like if you take a simple example of hydrogen atom, so energy is given by minus 13.6 by n square at ev. So for n1 and 2, you will get a well separated energy difference, but in case of 1000 and 1001, so the energy gap will be very small, very small. So rather describing a discrete state, it can be written as a density of a state. Okay, so now when n increases, n means your number of quantum state increases, the change of wave function is very less, and you can write the wave function as an average wave function. So now then if you shine the light, then total probability of transition can be written as into density of the state into du. Okay, so this is something new thing attached over here. It's known as density of the state. Now if we integrate it, then what we will get? Total probability E0 square 4h cut square omega a phi omega square. Now this will be sine square omega t by 2 omega square. So all the energy dependent part should be in a same position. Into now the thing is that what this integral says. So we know Now if we look at the expression of delta omega into t, it will be fi minus t, so it should be e by h cut now if we consider this is around x, so dx is equal to 1 by 2 h cut t to de, so de will be 2h cut by t dx. Now if we incorporate all of these things on the equation, it will becomes a0 square square 9 sine square x by x, say square. Now this part will come out and it will be, as you know, 0 to infinity we can write as a minus infinity to plus infinity to dx. So this part will come up to pi e0 square into 2h cut square omega fi by omega square if omega e I square t into pf. Okay, so now, so this is density of the state. So f omega, now coming back to the question, can f mu dot e cannot be considered as a constant under narrow energy region. It can be, it is constant because it's an integral form. It is constant in a narrow range of energies, because for high n values the change of the state is very minute. So you are not sure you are exciting from ground state to 1000 or 1001 state. So it can be in a high density of state, this value can be considered as a constant. So this is a correct one. Sorry, not wrong. So for high value, this for a if in density of state is constant. Now the number of states in the energy range E and E is given by P rho T. That's what I tell here. This density of state can be written as so this gap you can consider as a dT. Now the probability is time dependent. It's not. It is known. Now the change in wave function in a narrow band energy cannot be ignored. It can be ignored because you can see I told that there is so many in high quantum number value, the density of the state is so high, the change in wave function with excitation is is not uh, is not so significant. So when the state is embedded with in a density of state, the wave function can be written as an average wave function. So the change in wave function can be ignored. So this is incorrect. So for F in DOS, change in wave function can be ignored. Now moving to question number 4. So before moving to question number 4, let's complete something else, what is known as rate of transition. So rate of transition by another factor is nothing but total probability of transition by T. So rate of transition can be written as now in another way, the short form written by as 2 pi h cut mu square. Now the expression of mu square is the expression of mu square is d0 square 4 h cut square if so whole term is constant, and in the expression of rate of transition, you can see these all part are constant. So can be written as a constant into rho. Therefore the rate of transition is proportional to the density of the state. Now this is something known as very famous Fermi golden rule. Okay, so your total rate of transition actually depends on the density of the states present in a system. So now let's look question number 4. For the system in question 3, the rate of transition A5 is expressed as the correct statements among the following is or are: A. Rate of transition is proportional to the modulus transition dipole. That is now P, the rate transition is proportional to density of states. That is C. The above expression for A5 is referred to as Fermi golden rule. T, the rate of transition increases linearly with time. Now, the rate of transition, it's not proportional to the modulus, it's actually proportional to the square of the modulus. So it is incorrect. The actual answer is now the rate of the transition is proportional to density of the state. That is correct. Now the above expression WFI is referred to the Fermi golden rule. Okay. Now that the rate of transition increases linearly with time. So the thing is that there is say no such any expression of T incorporated with the rate of the transition. So therefore rate of transition is solely based on the density of the state and independent of time. Yes. WFI is independent of time. Okay. question 5. The rate of transition can be calculated by multiplying the square of modulus of the transition dipole moment and the density of states at transition frequency. Each of the following user are correct statements about the transition dipole moment. Is proportional the square of modulus transition dipole, that is omega a phi being the transition dipole is proportional to the density of state. That is C, the transition dipole proportional to the transition moment integral, that is So let's start with the same formula, 2 pi h mu square density of the state, where mu square is known as transition dipole having expression so from this equation we can tell W is proportional to square modulus. Second, mu is proportional to transition moment integral and also proportional to no, these are not. So what we can write, the rate of transition is proportional to the square of the modulus of transition dipole. That is correct or not? Now the transition dipole is proportional to density of the states, which is not correct. There is no transition in transition dipole expression. There is no density of the state, so therefore this is incorrect. Now transition dipole is proportional to the transition moment integral. That's what we saw here. Now selection rules are determined by the transition moment integral. That is correct, because nothing but this thing is correspond to the selection rule. Therefore transition dipole also related to the selection rule of electronic transition or whatever transition. Now since for the rate of transition between states 1 and 2, the population N1 and N2 respectively, the correct statements among the following there are rate of absorption, depends on radiation density and population of first state. The rate of emission depends on N1 and N2. C. Rate of spontaneous emission depends on the rate of stimulated emission. So now we came to a different part of the section where not only absorption, the emission is also be considered. Now, however, all the expression what we have derived using time dependent perturbation theory is talks about the transition from, let's say, state 1 to state 2 with population n1 and n2 via absorption of light and decays via stimulated emission. But in practical case, how if you excite a light and the molecule will not be in rest for long for large number of time in state 2, it will eventually decay. So there is another pathway of decay, that is something known as spontaneous emission. So on the other hand, it should be noted that the absorption is always simulated absorption, because without any light the molecule cannot excite. Okay, so molecule can be excited in a one way simulated absorption, but when it is in an excited state, it can either decay to the decay through simulated emission. That means light will hit the excited state molecule and get it deactivated, and otherwise the molecule is spontaneously decay to state 2 to state 1. Now this all thing has means this all the phenomena will be in thermal equilibrium, and they in a relationship at a thermal equilibrium where the rate of absorption will be equal to the rate of emission, and this formula is given by Albert Einstein. So at thermal equilibrium, you can segregate rate of emission to two parts. Rate of absorption can be written as summation of two different emission, rate of stimulated emission plus rate of spontaneous emission. Now the rate of simulated emission and spontaneous emission, so the rate of simulated emission for 1 to 2 we can write as 1 2, so it is nothing but transition from 1 to 2. Okay, now it can be either 2 to 1 by spontaneous or 2 to 1 by simulated. Now rate of absorption from 1 to 2 will be depend on number of molecules present at state 1, and there should be an coefficient which rate constant with transfer is 1 to 2 state related to the 1 to 2 state, and there should be a radiation density. So B12 is just a rate constant of absorption. So similarly, rate 2 to 1 at simulated emission, it's depend on n to number of molecule present at state 2, rate constant 2 to 1, and new radiation. But spontaneous emission will occur without having, that doesn't depend on the radiation density. If you excite a molecule, it is in excited state, it will be deactivated anytime. So that doesn't depend on the radiation density, it's only depend on how much population is there in the excited state. So it can be written A 2 to 1 to N2. So A2 to 1 is rate constant of stimulated emission, spontaneous emission. Now at thermal equilibrium we can write rate of absorption means V1 to 2 N1 new radiation equal to spontaneous emission from 2 to 1 plus simulated emission from 2 to 1. Now the expression of new radiation now becomes A21 into by B1 to N1 minus B21 1 N2. Now if we divide both with N2, what we will get? Now divide with A21 B21 now we know the rate constant for simulated emission and absorption are same, so we put which can be on the and whatever. And from Boltzmann population distribution formula, right? H mu by kBT. So the new radiation become A21 by B21 exponential H mu by kBT minus 1. Now from black body radiation can be written as 8 pi h nu cube by c cube 1 by exponential now if we equate these two equations then we will find a21 by b21 it's 8h pi cube by c cube, or we can write a by b only is 8h c. Okay, we will discuss it in the next question. Now let's finish the first question, question number 6. So rate of absorption is depends on the n1 and new radiation. That is correct. Now rate of the emission is depend on n1 and n2. No, rate of is only on the n2. Now the rate of spontaneous emission depends on new rad new but and n2. So this is wrong answer, because rate of spontaneous emission depends on n2 and not on new rad. Now the rate of simulated emission is dependent on new rad and n2. That is correct. Now in the 7th question, the correct expressions for radiation density new rad among the following is or are. Hello? Hello? Yes. Option 4 is rate of simulated emission. Is correct, na? Last option is correct. N2 and red. Okay. Pi HQ B1 to C. So first option is the black body radiation option, expression of black body radiation. So This option is correct. Now what is the second one? A nu 2. Radiation density is A21 into N2. Okay. B12 into N2. That is not correct, because B1, if we write B12, it should be N1 and this should be N2. So this is a correct wrong answer. Now what this is something that we did previously, this one. So if we take the formula, new radiation density is A21 into BA2, sorry, can you please switch off your mic? It's little bit okay. If you have question, you can ask. Just otherwise, it's okay. Now, what we did, we just divided up and down. So from Boltzmann equation, what we get? E to the power h nu by kBT. So new radiation can be written as A21 B12 h nu by kBT minus B21. So this expression is correct. Now what he says? Okay. So same equation, if we take B12 is equal to B21 equal to B and A21 as a, so we can write like that. B will be common, KT minus 1. These three are the correct option of the question number 7. Now something more interesting is coming. Now for a molecule AB whose dipole moment is along z axis and interacting with isotropic light, which of the following is or are correct expressions for the modulus of square of transition dipole. this is the question. So what we need to find out, for a molecule whose dipole moment is along the z axis but the light is isotropic, then what will happen to the expression of the z component of the square of the transition moment integral. So think like that, mu, the expression of mu is square is E0 square mu dot E and E dot mu are both same as the scalar quantity. Okay, so now, what the question is said, the dipole moment is along z axis, okay, but your light is isotropic, so it is partitioned to 1/3 in h axis, you can think like that. So mu square is only, sorry, yeah, yeah, can be written as so z 1/3 of mu square. So the expression of mu z will be E0 square uh, 12 h card square if mu z into I f square. So now only mu z component is interacting with the electric field of the light. Now this thing we can write as 1 by mu z dot E. So correct expressions are so this will be 1/3, that is E0 by 12 square, and this one, and fourth one, no, this should be 1/3. Okay, so B and C are the correct option. Now question number 9, for the system described in question 8, interacting with isotropic and non-monochromatic light. The correct expression for the rate of transition transition W1 to 2 So, in the last question, solving the last question, what we found. So, if a molecule having a transition, having a dipole moment along z axis interacting with the isotropic light, then the only the z component or a transition dipole will interacting. So the z component can be written as 1 by square mu z square mu z square is 1 by 12h cut square 1 root e1 square. Now we know the expression of transition from rate of absorption from 1 to 2 can be written as mu z square root 2 e. So the expression would be become pi by 6h cut 2 mu z e 1 to e. Now this is so E0 permittivity at free space. So 1 to 2 can be written as pi 6 epsilon 0 cut 2 mu z into e 1 square into e 2. See, so the whole equation is become like that. Now another now what they another condition that they set is non-monochromatic radiation. So non-monochromatic radiation radiation the radiation density in between nu plus d nu, so rho rad nu, sorry, total radiation density is radiation density integrated over whole d nu. Now omega 2, sorry, rate of absorption is omega omega 1 to 2 is pi 0 square e rad nu d omega. So for non-monochromatic radiation we replace the density of state with the radiation density. Okay, now pi, if we take E0 out, then it will be one by h cut rho at nu. Okay, now cuts 1 root JD 1 square to rho right angle. So this is the expression of rate of absorption. Okay, now so as a monochromatic radiation, we have to change the density of the state, because it's non-monochromatic radiation. You just excite as a particular state. However, this is embedded with another state. So there is no density of the state. So anything is connected to density of the state, or in this case is not correct. So remember, this non-monochromatic term is there. So in discrete transition, there will be no transition, no radiation density. Okay, so this is not correct, this is not correct, this is okay, then it's not needed. This is the correct option. Okay, moving to the last question of the session. For Einstein's coefficients A and B, the correct statements among the following is or are ratio of A to B is nothing but ratio of rate constant of simulated emission to continuous emission. B, ratio of A to B is directly proportional to the energy gap between ground and excited state. C, coefficient and B are directly proportional to transition dipole. D for large delta E values which means spontaneous emission dominates over simulated emission. Okay, so what we found that A by B is 8 pi h cube by c, but we don't know the expression of A and B. We have a relationship. So what we know, A is a rate constant for spontaneous emission. B is a rate constant of absorption or stimulated emission. Now, in previous question, what we solved, the expression of rate of absorption is pi pi by cut square 2 UZE 1 square into radiation density. Now what we know, this is also rate of transition from 1 to 2 is nothing but B1 to 2 N1 nu rad. Okay, so B1 to 2 you can write as a B. So B N1 is taken as a whole, is 1 nu rad 1 6 h cut square mu z into E 1 square radiation density. Now we can take these two out. So the expression of B becomes this. Now once we know the A, so expression of B is A is nothing but C to B. So expression of A so A will be 4/3 so it can be written as 16 pi square h cot square h nu c cube into pi into so now the whole formula becomes 8 pi cube pi 3 h sorry h this is and c cube, and there should be new cube into so these are the expression of coefficient. Okay, so both contain TMI. And A by B is proportional to nu cube. So rate of spontaneous emission by rate of stimulated emission so nu is somehow corresponding to the energy gap. So if a system of same molecule, so they have this thing constant. Now system 1 and system 1 and system 2. So this will be the delta nu 1 and this will be delta nu 2. So nu 1 is greater than nu 2. So as a result, so the A by B cube will be so if energy gap increases, the A becomes much more greater than the so for a system with larger energy gap, spontaneous emission dominates over simulated emission. Okay, these are all about the Einstein's coefficients. So now from this option we can choose. The first option is A and B is nothing but a ratio of rate constant of simulated emission of to spontaneous emission. So this is not simulated emission, this is A is corresponding to spontaneous emission. So first option is incorrect. B, A and B directly proportional to the energy gap. No, not directly proportional. A and B is the proportional to the cube of the A and B directly proportional to square of the modulus of the tangent dipole moment. That's what we see. So this is correct. And now the large delta E value. The delta E nothing but the delta mu value. The A much greater than B, which means spontaneous emission dominates over the simultaneous emission. So these two are the correct option. Okay. So with this we finish our task of our fourth assignment, and so I hope if there is any question you can ask me. Okay. Okay. So in the next session, from the next day, you will get a flavor how this all the derivation is connected to the experiment. So whatever we record in our absorption spectrometry, the plots and all, from the plots we can get the lifetime and all these things, which can be calculated using these all formulas. If you know the expression of the all these things, mu, wave functions of ground and excited state, the energy can be predicted theoretically, and that can be justified from the experiment also. So from the next lecture, there is a discussion how experiment and theory can predict the excitation and de-excitation phenomena. Okay, so with this I am stopping it here. Thank you.